So here's a very simple example. Use an iterated integral to find the area of the region and then check it with geometry. Well, I drew this picture in such a way that you could see if I integrated with respect to y first, then I'd want to have limits going from 1 to 6. Say 1, 2, 3, 4, 5, 6. And then with x later, I would integrate from 1, 2, 3 to 4. And it doesn't take rocket science to figure their answer is going to be 15. I just let my software evaluate that. But if I were to show you this in detail, our first thing to do would be integrate 1 dy. Well, that would just be x, right? X. And x would then have to be evaluated. Oops, sorry, not like that. Between, oh, I shouldn't have done it like that either. Well, I'll get there. I'll get this right. Oh, I don't want to do that either. I just want to say times there, yeah. And now I'll do this other thing, yeah. Okay, x evaluated between 1 and 6. So 1 to 6. And of course, that would just give us 5. 6 minus 1. So what we really then want to integrate is just 5 dx, and of course that would be 5x and then I'll keep doing that wrongly. That would be 5x, and x is going from 1 to 4, so 5 times 4 is 20, 5 times 1 is 5, 20 minus 5 is 15. So we do get 15, but I mean, golly, we knew that anyway because it's 3 this way and 5 that way. It's a rectangle. So that one wasn't all that spectacular, but it did come off with exactly what we expected.
Wow!
Yeah, right. So let's try one that's a little more of a challenge. Use an iterated integral to find the area bounded by the graphs of f of x equals sine of x and g of x equals cosine of x on the interval from pi over 4 to 5 pi over 4, and then sketch the region. Well, I did that first. I sketched the region as best I can, and what we're going to try to find is this purple region here, and then what we need to say is, well, our integrand is 1, and our lower limit, which one's on the bottom, is this blue one, and that's cosine of x, and what's on the top is sine of x, right? If you draw a stripe across that region, that'll give you the upper and lower limits. And then, if you think about starting this stripe at pi over 4 and finishing up at 5 pi over 4, that was really convenient since that is where these graphs cross. So those were some fairly convenient limits, but then pi over 4 to 5 pi over 4 are our x limits. From here, here's pi over 4 and here's 5 pi over 4 where these meet. It doesn't have to be where they meet. We could go from pi over 2 here, right, to pi if we wanted to do that. But this is kind of interesting the way it is. I'm not going to change it now. So integrating 1 with respect to y, we just get y. But then we put in upper limit of sine of x, lower limit of cosine of x. So it's going to be, instead of y, we'll have sine of x minus cosine of x. And we have this as our integrand now, and that's going to be evaluated between pi over 4 and and 5 pi over 4. So integrating sine, of course, we get negative cosine. Integrating negative cosine, we get negative sine. So this is going to be evaluated between pi over 4 and 5 pi over 4. So first of all, 5 pi over 4 going in first. Negative cosine of 5 pi over 4 is positive. Negative cosine, or negative sine of 5 pi over 4 is positive a half. Think of where that is. That's in quadrant 3, where the sign is automatically negative. This negative turns it around and makes it positive, the one right here. So that's the first part. And then minus we want to throw in pi over 4, so minus a negative, so it makes it plus 1 over the square root of 2, and same story with this, and there's another plus 1 over the square root of 2, so we have 1, 2, 3, 4 times 1 over the square root of 2. We could say 4 over the square root of 2 if we wanted to, but then we could rationalize the denominator by multiplying by square root of 2 over 2. We do wind up with 2 square roots of 2, and that is the area between these graphs.
Wow.
Yes, that is really special.